Okay, take 8. I fail at doing this. Okay, so I'm gonna teach you a little bit about the Rubik's Cube and the number of its possible permutations, which I guess is just one part because I can't explain anything. So let's say I have a Rubik's Cube, and everybody knows that the Rubik's Cube has like 43 quintillion permutations or something like that. And so what a lot of people haven't thought of is, why does it have exactly that number of permutations, right? This is a easy combinatorics question. So we've got to establish how we can put everything in such that we have a configuration. So how many ways? So let's establish first that the number of corners, we have 8 corners, right? So 1, 2, 3, 4, 8, right? So we have got 8 corners, and we've got 12 edges, 4 here, 4 in the middle slice, and 4 on the bottom. So we've got 12 edges. And so how many ways can we put them in here such that we have a unique combination? Let's start with the corners first. Let's start with corner permutation. How many ways can we just put the corners there? Right, so for corner permutation, there is 8 ways we can put the first corner in the first block. And then there are 7 ways we can put the corner in the second block, because we can't put it in the original 8th position because another corner is already there. And then there are 6 for the third corner, and so on and so on. So by that logic, the number of permutations for the corners is 8 factorial. And for the same logic, with all 12 edges, the edge permutation should be 12 factorial. Now, this is not the number of permutations for a cube yet, because we forgot to account for corner rotations and edge flips. So for any given corner, there are 3 orbits. There's orbit 1, orbit 2, which is this, and orbit 3, which is that. So there are 3 to the 8 ways to flip the corners, because they're all independent of one another. I can twist this corner, and it doesn't affect which way I twist this corner, right? So then the ways the corner flips are independent of one another, and it's different from this. And so that the number of corner orientations is 3 to the 8, and the number of edge orientations by the same logic, because edges can only be flipped or not flipped. There's no like 3 orientations of the edge. There are only 2. So by that logic, edge orientation, there should be 2 to the 12 ways to orient all the edges, right? But we're not done yet, because as some of you may know, there are impossible configurations of the Rubik's Cube. One of them is the edge flip, right? So for the edge flip, the reason why you can't do an edge flip, a corner flip, or a 2-edge swap is because there is something called parity within this group, and the parity has to be even. And if we flip only one corner or one edge, or only 2 edges swap the permutation, we'll have an odd parity. And we never want odd parity, because that means the cube cannot be, I can't return this to its original state. So basically we have to account for edge permutation swap, corner twists, and edge flips. So let's think about how many ways edge orientation, how many ways there are. So basically when you put the 11th corner in, put the 11th edge in, the parity is either even or odd. So even or odd, and we want it to be even, right? If we put it in one way, it'll be odd, and we put the last edge in one way, the parity will be odd. If we put it in another way, that the parity will be even. So whether the parity is odd or even depends entirely on how we put in the last edge. So therefore, there are only 1/2 ways that we can put in correct configuration, right? And for corner orientation, it's the same thing, right? So you can't put it in like this or this. The net result, you can't put the last corner in such that the net result is this or this. You have to do this, right? So you can return it. So basically, there are only 1/3 way correct configuration. There are only one third of the configurations are correct. Alright, for the edge flips, I didn't explain this properly, but for edge permutation, in fact, if you permute the edges wrong, you'll have something like this. And this basically means that whenever you put in the edge, let's say we're on the last two edges, right? And so this configuration is impossible. And so to get a possible configuration, you have to set the edge in a preset location, right? So if we think about edge permutation as 12 ways to put the first edge times 11 to put the second edge. So to put the 11th edge in, there's only one way. This is only one way to put it in. So basically only 1/2 of the edge permutations have correct configuration. So correct config. Okay. Alright. So now we have established the number of ways we can solve a Rubik's Cube. And it's fun. 8 factorial times 3 to the 8th times 12 factorial times 2 to the 12ths. And since only 1/2 and 1/2 of 1/2 of 1/3 of all those configurations is actually part of this group, which is the actual solved Rubik's Cube and not one of these twists or whatever, we have to divide all this by 12. And this is the number of permutations. Solvable permutations. And it's this. Alright. It's this. And that's like 4.3. Let me see. I have it written down. 4.3257. Just 10 to the 19th. Right? Okay, so now we've established the number of ways we can solve the Rubik's Cube. And now that we know this number, there is a surprising fact. We can establish the lower limit for the fewest solves that can be applied to the cube. Fewest number. Alright, lower limit for fewest number of terms required to solve. Right? And so basically what happens is that there are 12 turns, right? So you can either turn this way, clockwise. You can either turn one clockwise or one counterclockwise. And so what happens is that when you turn one clockwise, so there's 6 faces, right? And for each face, there are 2 ways to turn, either clockwise or counterclockwise. So there are 12 ways to turn the Rubik's Cube. There are 12 ways to turn the Rubik's Cube from an initial state, right? And let's say we want to mess it up some more. So basically, if we don't, basically one of the ways just turns it back, and that's the inverse of the operation we just did. And I might go into groups in another video, but this is the inverse, and we don't want that. So we can do this, just not this, because we returned it to the solved state. And so basically, it's 12 minus 1 ways to turn the cube now, right? And so that's 11 ways. 12 ways times 11 ways are the number of ways we can turn the cube. We can turn the cube from 2 moves, right? And so basically what happens is, so the number of ways that you can get from turning the cube, so n times, is 12 times 11 to the n minus 1. So this is the number of ways you can get after n turns, right? So basically, let's say that this number is greater than this number, which means that we have more configurations from here than we do from here, from turning the cube, just turning the cube to any state. And this means that we can apply the pigeonhole principle with this operation to this, and to find the lower limit of the fewest number of turns it takes to solve a Rubik's Cube. And if you're confused, you can just ask me later about this. But we can set up the inequality 12 times 11 to the n minus 1 is greater than 4.3257 times 10 to the 19th. And solving for n turns and ways. So this is the number of ways that the Rubik's Cube is configured after this turns, right? The number of configurations. And this is the actual number of configurations. So if we get n, we can find the lower limit for the number of turns on a Rubik's Cube. So if we solve for n right now, so 11 to the n minus 1, let me just solve it. Sorry, yeah, sorry about that. So, alright, so actually n is supposed to be greater than 19, but this experimental result is because this is not actually, this is an underestimate of the number of ways. This number is an underestimate of the number of ways it takes to solve the Rubik's Cube. This is just an approximate estimate. So this number actually is greater than or equal to 19, so the lower limit of the fewest number of moves to solve a Rubik's Cube is actually 19 moves. And we can establish that just by knowing the number of permutations, possible permutations here. That's an interesting fact. And I don't know, next post I might go more into group theory and how it applies to speed solving. Alright, thanks. See you later.